Hello guys, welcome to Romta Solutions and welcome to your lesson on work energy theorem as we continue with our series on work energy and power. So basically today we are looking at the work energy theorem. You will understand why we're saying network is equal to the change in kinetic energy and possibly try to derive this as well. So without any waste of time, we will define the work energy theorem and we will also have some examples. Okay, we will also have some examples. So let's begin. So we're saying we're looking at the work energy theorem, right? We're looking at the work energy theorem. So consider an object that's accelerating. Okay, and maybe let me write it. Consider an object that's accelerating on a horizontal surface. That's accelerating on a horizontal surface. Okay, so let me say this is our object, this is our surface. So let's say this is our object with its initial speed and then or initial velocity, and then it travels for some distance delta x or for some displacement delta x, and then we also want to find its final velocity or velocity at this point here. Okay, so what we are doing here, you remember that you can find the final velocity here by using equations of motion, right? You can find them by saying Vf squared equals Vi plus, I think it's 2a delta Vi squared delta x, right? This is how you can find velocity at this point here. Maybe let's call this one point A and call this one point B. So if you want to find velocity at point B, you can basically use this formula where you say this is Vf squared equals Vi squared plus 2a delta x, where the a is the acceleration of the vehicle, right? So now what if we multiply this? What if we multiply this by, maybe let's try to multiply by half m. Okay, maybe let us try to multiply by half m. When we try to multiply this equation here, should I call it equation 1? Yes. Let's try to multiply equation 1 by half m. Everything will be multiplied by half m. This means we will have half m Vf squared equals half mvi squared plus half m times this will be ma delta x, right? It'll be ma delta x. When you see half mv, this tells you that we are looking at kinetic energy, right? So this is final kinetic energy. Half mvf squared will be final kinetic energy, while half mvi squared will be initial kinetic energy. So let's simplify it. This will be Ek final is equal to Ek initial plus, this is ma delta x. Ma, I do remember that ma was from Newton's second law of motion. Ma was the net force, right? Ma was the net force. Okay, having said that, I do see that I have Ek sub E sub kf minus E sub ki, meaning final kinetic energy minus initial kinetic energy, equals F net delta x. I do see that this represents the change in kinetic energy, while this, I remember in the last video we said this is the net work, right? Because this is force times displacement. So this is the net work. Okay, so this now shows you that formula. Let me show you. In the opening section, we have derived this formula. Right? We have derived this formula. Remember when we were considering an object that's accelerating on a horizontal surface. Okay, on a horizontal surface. Okay, on a horizontal surface. Okay, so now we say, okay, we see you. So we have derived this formula here. So this formula is what we call the work energy theorem. Okay, this is the work energy theorem. Okay, this is the work energy theorem. Okay, this formula here is the work energy theorem. Okay, this is the work energy theorem. Now look at this formula. Now we're going to define it in words. In words, it says the net work done on an object, is equal to the change in kinetic energy of that object. The net work done on an object is equal to the change in kinetic energy of the object, is equal to the change in kinetic energy of the object. Okay, of the object. Okay, so from okay, let me write it again. So we say net work is equal to change in kinetic energy of the object. You know that this change in kinetic energy is basically kinetic energy of the final state minus kinetic energy of the initial state, right? Okay, so basically, maybe let me do it like this as well. This is EK final minus EK initial. Okay, so this is your work energy theorem. Okay, this is your work energy theorem. Right. So now you have ways of calculating your network. If your object is accelerating, if your object is accelerating on a horizontal surface, you can find your network. So you have 3 ways of finding your network. Now remember in the previous example it was only 2 ways. Now it's 3 ways. Okay, perfect. Now let us try examples. Let us try examples of the network. Okay, let us try examples of the network. So I'm going to try different examples. I'm going to try example 1. Example 1, let's say an object, okay, a 1.5 kilogram object is dropped. Okay, is dropped from 10 meters, right? From 10 meters above the ground. From 10 meters above the ground, right? So now I will say calculate calculate the work done. Calculate the work done. Calculate the work done on the brick. Calculate the work done on the object. Calculate the work done on the object between when it was released and when it hits the ground. Between when it was released and when it hits the ground. Right, between when it was released and when it hits the ground. And when it hits the ground. When it hits the ground. By the way, ignore air resistance. Okay, ignore air resistance. Okay, so initially this is your object, this is the ground. So this was 10 meters, right? And because it was dropped, it means initial velocity here is 0 meters per second, isn't it? Because it was dropped, it means initial velocity is 0 meters per second. Shall we say that? Yes, we can say that because it was dropped, right? Because it was dropped. So when it's dropped, obviously, from your knowledge of mechanical energy, this is basically velocity equals 0. Now, remember here, you are dropping, so it means your object is moving from this point to here. So at this point here, all right, so at this point here, what would be our height? Our height at this point here would be 10 meters per second, right? So we will have to use law of conservation of mechanical energy, isn't it? We will have to use law of conservation of mechanical energy because the question said we must ignore air resistance, right? Because the question said we must ignore air resistance. What do we then say? We then say, okay, we know for a fact that at this point here, kinetic energy is 0. So EKI is 0. However, EPI is mghi. And what is it? 1.5 times 9.8 times, what is it? Our initial height at this time, it is above the ground. It is 10 meters above the ground. So this is, let's see, 1.5 times 10 times 9.8. This is 147 joules, right? This is 147 joules, okay? This is 147 joules. Because we said we're ignoring air resistance, this means mechanical energy at this point is equal to mechanical energy at this point here, okay? Now moving on, we will say EM initial is equal to EM final, right? So what is mechanical energy initially? It was 147, right? It was 147 joules. So this means mechanical energy final, it's also 147 joules. But what does that mean for us? We know for a fact that what this means is that this is the kinetic energy, right? Because potential energy at this point is 0, right? Okay, so this is EK final plus EP final. However, we are basically saying the EP at that point is 0. Therefore, kinetic energy final is 147 joules, right? Now, remember what the question was saying. The question was saying calculate the work done on the object between when it was released and when it hits the ground. So basically, this is the network, okay? So this is the network. What is network? Therefore, network is equal to EK final minus EK initial, which is 147 minus 0. Therefore, our EK is 147 joules. Okay, our EK is 147 joules. Okay, so these are a bit longer, so I don't have to confuse you. Now you understand how we make our calculations, right? All right. Now, let us now try maybe a different example. Let us try a different example. Okay, example two, let's try, I will say again, calculate, maybe this one here. Okay. Let's say calculate the stopping distance. Okay. Calculate the stopping distance. If a 1,000 kilogram car travels at 16.7 meters per second and experiences an 8,000 Newton frictional force, and experiences in an 8,000 Newton frictional force when brakes are applied. Okay, so calculate the stopping distance. If a 1,000 kilogram car travels at 16.7 meters per second and experiences an 8,000 Newton frictional force, please fix that at force, experiences an 8,000 frictional force when brakes are applied. So first thing first, when you look at this question, they say calculate the stopping distance. So this means distance, delta x is unknown. But they say stopping distance. This means final velocity must be 0. I do see, however, that the mass of the object, the car in this case, is 1,000 kilograms. And its initial velocity is 16.7 meters per second. It experiences a frictional force of 8,000 newtons, right? So now we must ask ourselves a question. When we calculate this, we must ask ourselves a question. What other forces are given? Do we have any other forces given? And is it important to consider any other force? I do not think so. So it's okay. The only force that's playing a role here is the force of friction. So we'll say net work equals EK final minus EK initial. We do know net work here, we're considering frictional force delta x cos theta, because friction is the only force that's playing a role in this motion. And this is half mvf squared minus half mvi squared, isn't it? Perfect. Now, what we are going to do now is to substitute all the values we have here. Our frictional force was 8,000. So this is 8,000, guys, times delta x. So we do not know it as yet. And our angle, remember, I've always been saying to you, friction opposes motion. So it acts parallel to the displacement, but in the opposite direction. So it's 180 degrees. Finally, the object stops. So I can take this whole part to be 0 because it's stopping. Right? So it's 0 minus half. The mass is 1,000. What is the initial velocity? I think it was 16.7. It was 16.7. Yeah, it was 16.7 meters per second. So now what do we have? We have 8,000 times delta x cos 180 degrees. It's negative 8,000 delta x equals 5,000 times 16.7 squared. Let's see. So this is Oh boy. So this is one, let me, oh sorry, 500, not 5,000, 500. So this is 139,445, right? Oh, by the way, minus, okay, minus 139,445, right? When I divide this by 8,000, what do I get? I get 17.43. So this is 17.43 meters, right? So this is the stopping distance. Remember the question was saying calculate the stopping distance if a 1,000 kilogram car travels at 16.7 meters per second and experiences an 8,000 Newton frictional force when brakes are applied, right? So that stopping distance is 17.43 meters. Okay, perfect. So remember guys, you can use the work energy theorem for any situation. Okay, for as long as you know your data properly, you can use the work energy theorem. So a tip is for you to always consider, maybe draw a free body diagram, understand your terms, your initial condition and your final conditions, understand what information is given in those situations, and then you will be good to go. Okay, so this is how you attempt your work energy theorem, and stay tuned for more questions. All right, so there will be more practice questions that we will be treating together. Otherwise, this is it, and see you next time. Bye bye.